Welcome to the Explainer. So, have you ever used a Java framework, like Spring or Hibernate, and just marveled at how it all seems to work like magic? Well, you're in exactly the right place. Today, we're going to pull back the curtain and look at the hidden machinery that powers it all. It's a fascinating technology called reflection, and it literally lets a program look at itself in the mirror and change what it sees.
So here's our game plan for this explainer. First, we'll take a quick trip to a world without frameworks to really appreciate the problem they solve. Then, we'll dive deep into Java Reflection, the secret sauce that makes it all possible. We'll see how it pulls off automatic wiring and how it uses these secret agents called proxies. And finally, we'll talk about the costs of all this power and what's coming next.
All right, let's hop in our time machine. Before frameworks like Spring were a thing, building an application was, well, it was a real slog. Imagine you're building a massive Lego castle, but instead of having instructions, you have to create every single brick from scratch and figure out where it goes all by yourself. That's kind of what manual dependency management felt like. In this old world, your application's main method was basically the ultimate micromanager. It had to know about every single piece of your application, every single component, and exactly how to glue them all together. Just look at this line of code. It's a mess, right? You're not just creating one service, you're manually building its entire support system, piece by painful piece. You can see the problem here. This whole approach is super brittle. If you decide to change just one tiny part, you might have to go all the way back to the beginning and rewire everything. It just doesn't scale. And this, right here, is the exact pain point that modern frameworks were built to fix. But how? How do they just know what to create and where to plug it in? Well, the answer lies in this really powerful built-in Java feature called reflection. Seriously, it's like giving your program X-ray vision. It gets the superpower to look at its own code and even change it while it's running. This is the secret ingredient. So to put it simply, reflection lets a program inspect its own blueprints in real time. It can see its classes, its methods, its variables, even the private ones, and it can modify them on the fly. This is the core trick that lets a framework operate on your code that the framework knew absolutely nothing about when it was first written.
Okay, so to use this superpower, you first need what's called a class object. Think of it as the blueprint for any object in Java. You can get it directly if you know the type, or from an object you already have. But I want you to pay really close attention to that third option, loading a class just from its name as a simple string. This is the key that unlocks everything. It means a framework can read a configuration file, see a class name it's never encountered before, and bring that class to life.
And here's where the real power kicks in. Once you have that blueprint, you can ask for a specific tool, say a method, just by knowing its name. Then you can command that tool to run, or invoke it, on any object that it's compatible with. We're basically turning the very structure of our code into data that we can play with. This is the fundamental trick that makes all the other magic possible.
So now that we get the basic mechanism, let's see how frameworks use it to solve that huge wiring problem we talked about earlier. And that brings us to one of the most important features of any modern framework, automatic wiring, which you probably know better as dependency injection, or DI.
So how does this actually work? Well, when your application starts up, a framework like Spring basically turns into a detective. It uses reflection to scan all of your code, and it's looking for clues. These special markers called annotations, like @autowired. Think of them as little sticky notes you leave on your code. These notes tell the framework, hey, this class needs one of those, and the framework then builds a complete map of who needs what and does all that tedious wiring for you. It's amazing.
Okay, this is where we really pull back the curtain. This slide is awesome because it shows exactly how different DI styles map directly to specific reflection commands. So if you like constructor injection, the framework is using reflection under the hood to find the right constructor and call new instance. If you're using setter injection, it's finding and invoking that setter method. It can even use field.set to reach right into a private field and jam a value in there, totally bypassing the normal rules to get the job done.
I mean, the difference is just night and day, isn't it? We go from that complex, brittle, manual mess to a single, clean, declarative annotation that just says what we need. All that complexity just vanishes, managed entirely by the framework using reflection behind the scenes.
But dependency injection is really just the beginning. Reflection has another, even more mind-bending trick up its sleeve, the ability to create fake proxy objects on the fly. These are runtime-generated stand-ins that can intercept method calls to your real objects and add all sorts of cool behaviors.
So think of a dynamic proxy like a secret agent. It looks, talks, and acts exactly like the real object it's protecting.
But here's the cool part. When a call comes in, the agent can do extra stuff, like log the call or check security permissions before or after passing the message along to the real object. And the best part? Your code has no idea it's talking to an agent instead of the real thing.
Now in the Java world, you're going to run into two main types of these secret agents. The key difference is this. The standard JDK proxy can only work if your object follows a strict contract, an interface. For everything else, frameworks often pull in a third-party library called CGI-lib. CGI-lib is more flexible because it works by creating a subclass of your object at runtime. The only catch is it can't create a proxy for final classes, simply because you can't subclass them.
And this proxy technique is an absolute game changer for performance. Just imagine you load a user object from your database, and that user has like 1,000 orders. You definitely don't want to load all 1,000 orders just to display the user's name. So frameworks like Hibernate use a proxy. They give you a stand-in, a fake list of orders, and only when your code actually tries to access that list does the proxy agent spring into action and run the real database query. That's called lazy loading, and it saves a ton of resources.
Okay, so reflection sounds pretty amazing, right? It's this incredible superpower. So you might be wondering, why don't we just use it for everything in our own code? Well, like any great power, it comes with a price.
So why don't we build everything with reflection? There are three big costs. First, performance. It's just plain slower than a direct method call. Second, it breaks the rules. It can reach into your objects and mess with private stuff, which can make your code really unpredictable. And third, security. Modern versions of Java have been putting more and more restrictions on what reflection is allowed to do. And that performance hit is no joke. As you can see here, a reflective method call can be multiple times slower than a direct one. That's because the Java virtual machine can't do its usual smart optimizations. Instead of a pre-planned direct path, it has to dynamically look up the method every single time. Now, a few nanoseconds might not sound like much, but when a framework does this millions of times when your app starts up, that reflection tax really starts to add up. Because of all those drawbacks, the story doesn't actually end here. The industry is always evolving, and the latest generation of Java frameworks are finding some really clever ways to give us all that same developer magic, but without having to pay the performance price at runtime.
The new frontier is basically to do all the heavy lifting before the application even starts. So instead of using reflection at startup, these modern frameworks like Micronaut and Quarkus use something called annotation processors during compilation. They read all your little sticky note annotations and generate all the necessary wiring and proxy code ahead of time. So you, the developer, get the same clean, easy experience, but the final program that actually runs is just plain, fast, optimized Java code with zero reflection tax. So here's the main takeaway. That magic in your favorite frameworks, it's not magic at all. It's just really clever engineering built on this powerful foundation of reflection. And by understanding this one concept, you've unlocked a much deeper understanding of how these incredible tools really work. So now that you've seen behind the curtain, what other software magic are you curious about? Let me know in the comments below. Thanks for watching.